Okay, very good evening from India. So I am an isotope hydrologist by profession. I use water isotopes to study various physical processes operating in the hydrologic cycle. And with this, I try to quantify the extent of some of these processes in the modern times and how it was in the past. So this is my group. Along with that, there are many master students who has also contributed to this work. So this is the outline of my talk. In first few slides, I will be talking about the application of the stable isotopes in hydrology and climate change. And then I will discuss about how do isotope values changes in the hydrologic cycle. Next, we'll discuss about the water isotopes in the Indian summer monsoon, why it is so important. Then how are the water isotopes simulated in the models? Mostly I will be talking about the general circulation models. Then how accurate those models are. And lastly, I will be showing the 3 case studies, which is our own work, which will be discussing how the models work with the observation. So we did observe, or we did our own observations, and also we have seen the performances of some models simultaneously in 3 different time scales. So in the daily time scale, we'll see in one study, weekly in another study, and monthly in the last study. And then there will be some open questions. So this is the application of stable isotopes in climate change study. When we study the climate change using high resolution proxies, like say speleothem or tree ring, they tell you the information of the past, say in a frequency or in a resolution of 1 year, 2 years, or something in that scale. It can goes to even 1,000 years to 3,000, 4,000, even 10,000 years long. So we study the oxygen isotope of these proxies in the tree ring cellulose or speleothem carbonates that we study basically. So when we interpret the climate changes during the say last 1,000, 2,000 or 10,000 years using these proxies, we had some assumptions. So what assumptions we have? That these isotope values of these proxies, they are actually was in equilibrium with the rainwater from which these proxies form. So this is number one assumption. And second thing is that the isotope values of this water at that time, they bear some correlations with some of the climatic parameters. It could be rain amount, it could be temperature, it could be humidity, but they are related. So if we know the relation between the climatic parameters and water isotopes of that area, so these relations we can actually use to understand the connections between the isotope values of those proxies and the climatic parameters of that period. That is actually the principle of the reconstructions. So in that way, the water oxygen study is water isotope studies are very much useful. So this is the water isotopes that we study generally. These are all stable isotopes. As we all know that water has 3 stable isotopes, 16, 17 and 18. 2 oxygen, 2 hydrogen stable isotope it has, like deuterium and protium. So we in the instrument, which is called either it is the isotope ratio mass spectrometer that we have, or we have a laser water isotope analyzers. In both these instruments, we measure the heavier to lighter isotope ratios, and we express the oxygen isotope values or hydrogen isotope values in terms of delta. So this is the parameters that are very useful for water isotopes. Along with that, there is another parameter which we call dxs, which is actually a combination of the oxygen and hydrogen isotopes. So these 2 parameters are very useful to understand the evaporating condition of the moisture source, how the moisture transported along the path, and the rain mechanisms. So these are the informations that we can get from water isotopes. It can be rain or it can be vapor isotopes. Then whatever the observations or whatever the knowledge we get, we try to put it into some general circulation models. So these models actually simulate the water isotopes, considering how the atmospheric circulations control the isotope values. So before going into the detail of the models, I'll tell you how do water isotopes fractionate, or in a layman language, I can tell how do water isotope changes in the hydrologic cycle. So this cartoon is very much known to you all. we all know this is hydrologic cycle. So every time there is some phase change, there is some change in the isotopic values. So you can see that there are different combinations of H2O molecule that can be produced using the different heavier and lighter isotopes of oxygen and hydrogen. And they have different natural abundances also. So the thumb rule here for these all processes is that lighter isotope prefer to go into the lighter phases and heavier isotope prefer to remain in the heavier phases. So suppose water is evaporating from ocean, so the vapor will have more lighter isotopes compared to the ocean. So definitely, as per the delta values, the definition, we can see that the isotope values of the vapor will be more negative than the ocean from which it is forming, but the evaporation of the ocean from which it is forming. So fractionation is the term, actually we call it, that is the distribution of heavier to lighter isotope ratios during different phase changes. So isotopic fractionation during phase change in the hydrologic cycle has been shown here. So the water isotope values which we get finally, it is actually suffering the fractionation of all these processes, right from ocean, evaporation, transport, precipitation, formation, condensation, then precipitation. Evaporation also takes place during falling to the ground. Then it can be mixing with the local moisture balancing from local lake, rivers, etc. So the final rain samples that we collect at the station is basically giving the basically showing you a picture of how the fractionation takes place during the entire hydrologic cycle. So now the isotope rain amount or temperature or moisture circulation, these relationships, what we get in the present days water samples, those are used for paleoclimate reconstruction, mostly temperature and rainfall. So when we talk about the rainfall, now we go to the Indian summer monsoon rainfall. So let us see what water isotopes in Indian summer monsoon tells. So before going into that, what is Indian summer monsoon? Why the water isotope studies of Indian summer monsoon is so important? Monsoon, as we all know, it is basically a major wind system that seasonally reverses its direction. So in one time it is flowing from, say, for India, it is flowing from southwest direction in one time and from northeast direction in another time. So Indian monsoon is actually the most prominent of the world monsoon system, which results in copious rainfall over India and the adjoining ocean, and it controls the agroeconomical development of the country, of the entire South Asia, we can tell. So the moisture sources, rain mechanisms are entirely different for the two monsoon that we experience here. So earlier studies have documented that the water isotope values are entirely different. Both the delta 18 or delta D or DXS values, they are pretty much different during these two monsoon season. So it can actually preserve the signature of a particular monsoon system that is occurring here. So after in our study, in my study, I will be showing three such case studies, as I told earlier, for southwest monsoon only, that how the observed data varies or how they are actually replicating the hydro-meteorological processes in daily, weekly, or monthly time scale. So before going into our own work, I will be, as I have told earlier, that I will be comparing our observed data with some existing models also. So let us spend 1 or 2 slides about what is general circulation models which are isotope enabled. So isotope enabled general circulation models, they basically simulate these all isotope ratios that we are discussing so far, using all the considering all the physical processes like evaporation, moisture advection, diffusion, convection, and evaporation. So all these processes are taken care into the model, and after considering all these processes, they basically simulate the water isotopes. So isotopes in general circulation model, in a very simplistic way, it is an atmospheric general circulation model, which we often use for rain prediction of rainfall, prediction of temperature, etc. So these are the atmospheric GCM over which there are several isotopic parameterization schemes that is also involved. So isotopic parameterization schemes, they actually take care of all the fractionation that I showed happens in the hydrologic cycle. So these parameterization schemes are incorporated into the model. Some of the parameterization I am showing you, these are the equations that the model follows for say ocean evaporation, during condensation, during raindrop evaporation, and finally they give you the delta G and delta AT, that is the hydrogen and oxygen isotope values of the rain and vapor. So that is what the general isotope enabled general circulation models work. Now, how realistic or how reliable are these isotope enabled general circulation models? So here the observed and model values are compared. This is the observed values are taken from the global network of isotopes in precipitation, which is actually a global network of International Atomic Energy Agency. They have some rain sample collecting stations all over the world, where mostly the monthly composite rain samples are collected, say for 30-40 years in some locations also. And these data, along with that, the co-located model values are compared. So if you see these plots, you can see that the observed and model isotope values are well correlated. There is a tight correlation. Say correlation varies from 0.84 to 0.91 in the annual time scale and 0.75 to 0.6 in the seasonal time scale. But there are many lacunae in these models are also there. Some of the issues is there that there are the isotope biases. That means the model minus observed values, they vary a lot. Especially they vary from 1 to 11 per mil, which is quite significant for oxygen isotope over the extratropical region. And second lacuna of this model is that the marine boundary layer vapor isotope is very poorly simulated. In Indian summer monsoon, although I told you that it is a very important monsoonal phenomena, very less studies have been done till date, which actually compared the observed and model isotope values. Only one study presented so far, they showed that there is a good correlation between climatological monthly mean. I mean the long-term monthly values, they show a reasonably good correlation with the observations. So this is the one study, but there are many questions that are open, which has not been solved yet. Number one, how the model isotope variability takes place over the period in comparison to the observation. Secondly, which factors controls the isotope bias, or more simplistic way, which factors depart the model values from the observations and how much, or whether we can make some quantitative assessment. Then actually we can improve the isotope enabled general circulation model simulation, which can improve the climate modeling in future. So these are some of the open issues which will be discussed in subsequent slides. So now, as I told you that water isotopes are collected in the different frequencies. So depending upon the frequency of the sampling, this data set can preserve the signature of different events. Like if you have a 30-40 years data, mostly the International Atomic Energy Agency they have. So if you have a 40 years, 50 years data set, it may capture the signal of the ENSO or El Nino. So this can be captured, but if you have a higher frequency samples like what we did in our cases, which is daily or event based sampling, so it can even capture a periodic events which is more highly frequent, like some intraseasonal oscillations, like Maiden-Julian oscillation or monsoon intraseasonal oscillation. So this is our study in Andaman Nicobar Island in 2016. There we found that the isotope values capture even 10 to 20-day periodicity. So these all depend. So what signatures the water isotopes will preserve, that entirely depend upon the frequency of sampling. So now there are again some open questions that there, like monsoon intraseasonal oscillations. Even within a intraseasonal oscillation period, the intraseasonal oscillations, let me discuss what it is. It is basically a periodic movement of convective clouds as well as rainfall over the Bay of Bengal. So if you analyze the daily rainfall data set, you will get a periodicity. So this periodicity can be captured in the isotope values. But there are many questions which is not answered yet. Even within a convective event, you can get a large variation of the water isotopes. What results this? We don't know. Is the long-term isotope variability solely controlled by the intraseasonal oscillation, or it captures some local phenomena also? that is also we are going to study in our cases. And secondly, how general circulation model captures these rain isotopic signatures of the intraseasonal oscillation in comparison to the observation. So these are some of the issues that will be discussed. So the first case study which I am discussing, that is the daily scale. So intraseasonal variation in observed and model rain isotope data on daily scale. Here we collected rain isotope samples for say last 10 years. It is a period of 2004 to 14. We collected samples from some location in eastern India. These are the two locations from where we are collecting. This is a daily sample, so you can understand there are total 700, 800 samples that we have analyzed, and all the samples are analyzed by isotope ratio mass spectrometer. So if you see the results, you can see there is a large variation of water isotopes in different year. So these are all summer monsoon, Indian summer monsoon, which is roughly the period covering from June to September of each year. So one can see there is a large variation of oxygen isotopes from minus 18 per mil to even 2.8 per mil, where the hydrogen isotope varies from minus 130 to even 29 per mil. So usually we consider that the heavier rainfall events is always associated with a more lower isotope values. But when we plot the local rainfall values, we can see that lower delta values are not necessarily associated with the heavier rainfall event. So there must be some other processes which is triggering the isotope lowering over our region. So that is something what we are going to study now. So this is the OLR anomaly that we have plotted here. So OLR basically it is an indication of the convection. So one can see that how the convection takes place over the Bay of Bengal and how it propagates from say 5 degrees south to a coastal location at 20 degrees north. So one can see that the depletion or the negative isotope values we get only when these convective events are reaching towards the coast. So what we can say that the 16 convective phases of the intraseasonal oscillations that we have identified in our study period, and there is a large variation even we obtain within a particular convective events. Now the question remains why we get such a large variation of isotopes even within a convective event. So this will be discussing later on, and this is actually what we call the convective phase speed. It is basically the tracing of the convection bands from 5 degrees south to 20 degrees north in our cases. So if I can go to the previous slide, you can see the convective bands moving from the 5 degrees south to the study region that we are tracing. So we can see that when the convective band is reaching to our sampling location, that time actually we get the lower isotope values. These are the cases. So it doesn't depend on the local rainfall. It depends actually the total rain out over the entire ocean or entire bay. So when we make a correlation between the speed means the speed with which these convective clouds are moving over the ocean, we found that there is a strong positive correlation between the oxygen isotope and the phase speed. And also we found there is a strong negative correlation between the cumulative rainfall occurring during those events over the ocean and the isotope values collected at the coast. So these are all coastal locations. So which means that more faster the bands are moving, more less rain it takes place over the ocean. So resulting isotope values at the coastal locations are quite enriched. But if the convective bands are quite slower over the ocean, then it takes a huge rainfall over the Bay of Bengal and relatively the isotope values are more negative. So this is all the observations that we got from our 10-year long data. Now we want to see how the models are performing. So here we have taken a model, isotope enabled global spectral model, ISO-GSM. So when we compare the isotope values, considering all phases and considering only during the convections, we found the results show a very weak correlation. Say R is coming around 0.39 or R is coming around R.42, which indicates that the simulation, although it is showing somehow capturing the mean values, the day-to-day variability is not properly captured in the model. Then we plot another parameters called stratiform fractions in cloud, which generally bear a negative correlation. So if you have more stratiform fraction, we'll get more negative isotope values. So which is pretty well found during our observations. So when we compared the stratiform fraction with delta, we got a reasonably good correlation, negative correlations, but in model we found the correlation is very weak. So the conclusions we draw here, that oxygen isotope variability within convective phases of meso depends on the rain amount and the phase speed over the Bay of Bengal. It may not depend much on the local rainfall amount or the local meteorological parameters. Secondly, apart from meso, there are other controlling factors like stratiform fraction that also contribute to the delta 18 variability over our region, although model could not simulate this relation reasonably good. So ISO-GSM simulated rain values weakly correlate with the observed values as well as the stratiform fraction. So this is some of the conclusions that we make from our daily scale observations. Now let us come to our weekly scale observations. So we collected 2 years of weekly samples of rainwater isotopes, and one can see that there is also some significant variations during the summer monsoon, although the magnitude of variation is less compared to the daily one. It is quite well expected because in weekly composite samples, actually we allow the water samples to stay there or stay in the container for say 6-7 days. So definitely we get a average signature of the daily phenomena. So definitely the magnitude of variation will be smaller. So similar trend we found in 2 different years. Then we compared our value with the weekly composite samples or the monthly composite samples collected from a IAES observatory at New Delhi. So we found that all the cases, both the locations, why we compare with the New Delhi? Because this is a location which is fall on the same monsoon track, which is starting from Kolkata, say at the coast, and New Delhi is on the inland. So when we compare a coast and an inland station, we found that the variation show the similar pattern. So, but the New Delhi receives more depleted rain in 1 month prior to Kolkata. So, important phenomena. Another thing what we found, that the maximum rainfall and the minimum isotope, they have a 2 month of phase lag. So they are not working tandem. So most of the cases in the paleoclimate study, we use a negative delta 18 isotope correlations of the local correlations, which may not be valid everywhere. So that is what we found in our region. So then actually we estimate some of the parameters. I'm not going into the detail of that. We compared their value, we made some advection model, and we showed that along the track from Kolkata to New Delhi, the New Delhi moisture also gets a multiple sources apart from the Bay of Bengal, that is Arabian Sea. In addition, they found that another moisture is coming from the evapotranspiration along the track. So these are some of the models that we did. So now, after daily and weekly, the last study is on the monthly scale. So how do observed and model isotope data vary in monthly scale? Here actually we considered it is not our data, it is the data from the observatory of International Atomic Energy Agency. So there are different locations are there. We grouped it as so Eastern Coastal India, Western Coastal India, and Northern India. We made it 3 groups. So there are 9 stations total we consider here, and we consider also 1, 2, 3, 4, 7, 8 models. So to see how these models capture the observed isotope values in the different region. So this is our very latest study that published in Climate Dynamics. So here, this is the models that we have considered. There are some free models, there are some nudge models also. And this is the observed data set that we have considered. They are all International Atomic Energy Agency data. Apart from that, we also consider vapor isotope data from tropical emission spectrometer. So this is available from 2005 to 7. Observed and model isotope data from these locations for all summer monsoon months, synchronous time periods with the observation are merged as per the different subregions: eastern coastal India, western coastal India, northern India, and the biases are estimated. So if you see the del 18 values, these are the mean values. The mean biases are plotted, that is the model minus observed isotope values are plotted in the different subregions, and this is their correlation. So one can see the del 18 values are largely or marginally underestimated in the west coast for all the models, but there is no systematic trend we found for northern India. High correlation is found only for limited models. Otherwise, the correlations with observation and model are generally low. So this is some of the isotope climate parameters correlations that we studied in the observation. So GNIP is the observation and other are the models. When we do not see any negative correlation between amount and isotopes in the observations, many of the model actually showing significant negative correlations. So one can say that isotope amount correlation is actually over interpreted in the models or overestimated in the model. Now the question comes that is the rainfall bias solely contribute to the isotope biases? So here we plotted rain, isotope biases and rainfall biases. We can see there are some limited occasions for limited models where we get a negative correlations, where increasing overestimation of the rain amount is actually connected to the underestimation of the rainfall isotope values, but it is not applicable to all models in all regions. So which factors actually control the isotope biases? So we also plotted the isotope biases with temperature biases, how the model actually estimated temperature, what is the true temperature, what is their differences, and whether these differences has any bearing on the isotope values. We again found some station specific correlations, but overall there is no general trend. So this indicates that the departure of these models from the observation is actually controlled by no single parameters. There are multiple parameters that are simultaneously controlling the isotope values and which also even vary from model to model. So isotope value biases in a given region result from biases in the physical fields in the other regions. So these are all the local parameters that we plotted. So next we'll see that how the regional scale atmospheric circulation controlling the isotope biases. We can see that this is the two locations we chose. One is the South Indian station Kozhikode, which is very close to Arabian Sea, and second one is the New Delhi, which is in the monsoon trough from which is extending from Bay of Bengal to the northern India. So this station shows some negative correlation with the isotope biases. So if the models actually they are underestimating the rainfall over the monsoon trough, which is actually resulting overestimation of the isotope values at New Delhi. So the isotope biases at New Delhi seem to be significantly controlled by the biases of the specific humidity, rainfall amount, wind, moisture transport over the monsoon trough region. So we found now that the isotope, the departure of the model isotope values from the observation, it not only depends on the local parameter, it depends upon is over or underestimating the regional scale atmospheric circulation also. So here we are trying to do a quantification. Say there are we are comparing the observations and model isotope values at 4 occasions. We did it for a station only for Kozhikode, which is situated close to the west coast. So west coast, let me show you the location. So this is the place where Kozhikode exists. So we made some box here, box A and B, and we actually compare the observed and model rain and vapor isotope values in the 4 occasions. One is vapor isotope value right at the surface over the Arabian Sea. Secondly, between 1000 to 600 millibar height over the source region, the vapor isotope values from sampling to source region, and then over the rain isotope values over the sampling region. And you can see that the models reasonably capture the vapor isotope values over the ocean, but it has a large differences among the models when we compare the 600 millibar vapor isotope values. So it indicates that the major biases, so we can go to the final things, that you can see that this is the quantifications we made, this is the observed quantification, and this is how the model performs in the different phases right at the sea at 600 millibar over the sea. That is the 600 millibar over the rain sampling location. This is the liquid that form over the rain sampling location, and this is finally which is the rain isotope values that we collected at rain sampling location. So you can see this is the departure of the model values compared to observations. So one can see here that the major biases actually are coming from the mid troposphere. So models, we conclude here that the efficacy of these models mainly depends on how effectively the model captures the mid-troposphere values. So the model which captures the mid-tropospheric vapor isotope values is the model which capture the rain isotope values finally. And secondly, we also made a raindrop evaporation model, and we see that these models biases are originating also due to the difference in their rain evaporation scheme. So these are the two parameters which needs to be actually improved in order to get a better simulation. So this is our conclusion from the monthly one, and daily and weekly one I have already discussed earlier. So thank you.